Okay, section 5.3, trig functions of angles. So in 5.2 we talked about trig ratios for acute angles in right triangles. And here in 5.3 we're going to try to extend these trig functions to angles that are not acute, angles that don't fit inside of a right triangle. So kind of reviewing the picture for an acute angle that sits inside a right triangle, we called the sides the adjacent, the opposite, and the hypotenuse of the triangle. But what we're going to do is take this triangle and put it into standard position. That is, we're going to put the adjacent side on the x-axis. And when we do that, this point P lies in the xy plane, and it actually has x and y coordinates. And the opposite side of the triangle now has length y. The distance from the x-axis up to the point x comma y is y. And the adjacent side of this right triangle now has length x, right, and corresponding to the x coordinate of this point. So what we can do now is, and the hypotenuse now, if you like, you can rewrite the hypotenuse with the letter r, where by the Pythagorean theorem, r is the square root of x squared plus y squared. Okay, so with this relabeling of the sides of the triangle, now we can relabel, redefine the sign. We used to say opposite over hypotenuse, but now we can say it's the y coordinate of this point divided by the distance from the origin out to this point, so y over r. And cosine can be x over r, and tangent can now be y over x. So we're redefining the three starting trig functions now in terms of the coordinates of this point P. Okay, so with that change, now we're ready to talk about what happens when the angle is no longer acute. So this is the picture that we were just looking at above, and now with the little slider here, we're going to let the theta, which is currently less than 90, let it go above 90. Okay, so when theta goes above 90, well, the first thing you notice is that this angle theta is no longer inside a right triangle, and that's why we need to do some other kind of definitions for the trig functions of this angle theta. And what we do is simply stick with the definitions that we just talked about, the definitions of the trig functions in terms of the xy coordinates of this point P and the length of this line segment from the origin out to P, that length being the labeled as r. Okay, so now we're going to think of sine theta being y over r, cosine theta x over r, and tan theta y over x, all in terms of this point P up here. So the first thing to get used to is that now the trig functions are no longer always going to be positive values. In the first quadrant, that is when theta was acute, these ratios all turned out to be positive, and that's because x and y were both positive, and this distance r is always positive. So in quadrant 1, the first quadrant, all three of these trig functions are positive, so all positive in quadrant 1. In quadrant 2, well, again, remember, we're defining in terms of the coordinates of this point. And in quadrant 2, you have to remember that the x's are negative. The y's are still positive, but the x's are negative. Okay, so r is always positive. So the sine, well, in this quadrant, the y is positive, r is positive, so the sine will be positive. The cosine, well, in this quadrant, the x is negative. A negative over a positive is negative, so cosine will be negative. And in this quadrant, quadrant 2 again, x is negative and y is positive, so this ratio is negative. So in summary, out of these three functions, only the sine is positive in this quadrant. The cosine and tangent were both negative. Okay, Quadrant 3, do the same sort of thing, except now in quadrant 3 we have to realize that both coordinates, both x and y, are going to be negative. So sine is going to be negative because y is negative. Cosine is negative because x is negative. But the tangent will be positive because a negative over a negative is a positive. So in this quadrant, only the tangent is positive. The other two are negative. All right. Last quadrant. So here we're to the right of the y-axis. This means that the x's are positive. We're below the x-axis. This means the y's are negative. Okay, so y's are negative. That says sine is going to be negative. X's are positive. That says cosine will be positive. X and y have opposite signs, so the tangent is going to be negative. So in summary, quadrant 4, only the cosine is positive. Okay, so here's a little memory aid for what we just reviewed here. So this little diagram is telling us which functions are positive in each of the each of the 4 quadrants. Which of the 3 functions are positive in each of the quadrants. So there's this little memory aid to remember this, this pattern. All students take calculus. I don't know if that's true or not, but that's the little mnemonic that we have. So just as an example, in quadrant 2, we take all students take calculus. S is what's in quadrant 2. This is that the sine is positive in quadrant 2. And remember, this is telling us that only the sine is positive. So that tells us also that the tangent and the cosine are going to be negative in that quadrant. Okay. Here are the first 2 new values that we're going to compute the trig values, trig functions for. Angle 0 and angle 90, or pi over 2. These are not acute angles, and so the trig ratios really didn't work for the right triangle trig ratios. Okay, so I'm trying to show a picture here where the theta is almost down to 0. We can barely see the letter theta anymore. But what I want to imagine is that when theta finally does equal 0, what are the coordinates of this point P? Okay, so when theta finally hits 0, the x-coordinate becomes r, simply the length of this line segment, and the y-coordinate becomes 0. That's a 0, not an O. Okay, so now we're going to compute the sine of this angle, 0. Okay, so the definition now, remember, is y divided by r. Well, when the angle is 0, the y is 0. So sine of 0 is 0. For cosine, that's x over r, and at angle 0, the x is equal to r, so cosine of 0 is 1. And lastly, the tangent of 0, that's y over x, so that's 0 over r, and so that'll be 0. Okay, so 3 new values to add to our table. And then at the pi over 2 or 90 degree, so again, I've tried to show that right before we hit 90, this is what the picture looks like. And as we finally come up and do in fact hit 90, the x-coordinate of this point P up here will finally drop down to 0, and the y-coordinate will match the distance out to the point and become r. Okay, so going through this again, the sine of pi over 2 now, we'll compute sine of pi over 2, y over r, well, the y will be equal to r, so sine of pi over 2 is 1. The x will be equal to 0, so the cosine comes out to be 0, and the tangent will be r divided by 0, and this is undefined, so not defined at pi over 2. Okay, I'll put a timestamp here and talk about steepness of special angles. 940. Oh no, T40. This is 940. Okay, so the angles that we're going to be trying to memorize special values for. In degrees are 0, 30, 45, 60, and 90, and in radians, these radian measures here. And it's really good to be able to quickly translate between degree and radian measure for these special angles. We've got conversion formulas. We know that we can take degrees and multiply by pi over 180 and it'll turn it into radians. But it's really best just to have these pairings memorized. And when you do that, it's also nice if you can attach to them a description. And what I'm going to call this is the steepness of the angle. So at angle 0, I'm going to call these angles the flat angle. And then the next angle up, the 30 and pi over 6, these are shallow. And the next at 45, we're going to call these medium. And then 60 degrees, aka pi over 3, those will be steep. And then the vertical will be the 90 and pi over 2. So it's just good to be able to refer to these measured angles with their descriptor of steepness. Start at flat, go to vertical. Okay, so for what it's worth, I will tell you that what I usually do to try to recall these special values of sine and cosine for these special angles. So remember that in the table, the sine and cosine always have one of these 5 values. And here they're listed from small to large. 0 up to 1, and they're in order. So what I like to think about is this idea of steepness. And the idea is that as the angle gets steeper, we see that the y-coordinates are getting bigger. So if the y-coordinates are getting bigger, that means that the sine of the angle is getting bigger, because sine depends on y. So for sine, as the angle gets steeper, the sine should get bigger. And that's why it starts out at the smallest value when the angle is flat and works its way up to the largest value when the angle is vertical. For cosine, things work the other way. The steeper the angle, the smaller the x-coordinate becomes. Right? When the angle is flat, the x-coordinate is as big as it can be. But as the angle starts to get steeper, the x-coordinate gets smaller and smaller. So the cosine is the function that depends on the x-coordinate. So the steeper the angle, the smaller the cosine should become. So the cosine starts out at 1 when the angle is flat and works down to 0 by the time the angle goes vertical. So if you can remember that association, the table of memorized values comes down to this. Think of the angles as going from flat to vertical. Remember that the sine is connected to the y-coordinate, and when the angle is flat, the y-coordinate is 0, and the y-coordinate is getting bigger as the angle gets steeper, and vice versa for the cosine and x-coordinate. And then the other columns in the table, try to compute them like this. Okay. Not really in the text, but I will continue to refer to angles as flat, shallow, medium, steep, and vertical, so I wanted you to know what that was referring to. Okay, reference angle. So here it is in the blue box. For an angle theta, the reference angle is the angle between the terminal side and the x-axis. So this theta bar is the angle between the x-axis and the terminal side of theta. I think the pictures are doing the best we can here. Here's the angle theta. Here's the terminal side of the angle. So theta bar, the reference angle, is the angle between this terminal ray and the x-axis. Okay, so we're going to talk about computing reference angles, but to do that we have to be sure we know what angles correspond to the x-axis. We're trying to measure angles between the x-axis and something. So in radian measure, odd multiples of pi, 3 pi, minus 5 pi, those are all coterminal with the negative x-axis. And the even multiples of pi, 2 pi, 0 pi, minus 6 pi. Those are all coterminal with the positive x-axis. In degree measure, odd multiples of 180. 180, it's hard to do. I guess maybe 3 times 180 is 540. Those are coterminal with the negative axis. And the even multiples, 360, 720, those are coterminal with the positive x-axis. Okay, so with that in mind, let's find a reference angle. Find the reference angle for 135 degrees. Okay, so 135, we need to measure to the x-axis. The negative x-axis is at 180, and that's the closest x-axis we can get to, the negative side. So 180 minus 135 is 45. That's the reference angle for 135. Okay, so we're going to use this reference angle now to compute the cosine of 135. Okay, so here's the picture. Angle 135 is over here. The reference angle is 45. But we've also drawn the reference angle over here as an acute angle that we're more familiar with, an acute angle in a right triangle. Now there's a symmetry in this picture that says if the point here has coordinates x comma y, the corresponding point over here on the angle 135 has got the negative x, same y but negative x, right there, at the same height but they reflect across the y-axis. Okay, so if we remember our recent new definitions for cosine, cosine of 45, it's the x-coordinate of the point divided by the r here. So this would be x over r. For cosine of 135, it's the same rule. We have to take the x-coordinate of our point, but now the x-coordinate is negative x. It's the opposite of this x-coordinate. The radius is still the same. I should just say the r. So what we're seeing here is that cosine 45 and cosine 135 have opposite signs. One is simply the negative of the other. So this tells us that cosine of 135 will be the opposite, that is the negative of cosine 45. Now, cosine of 45 degrees, what I want you to try to remember, and you can also just look this up, but remember that 45 degrees, that's the medium angle. And that tells us that this should be the medium of the 5 possible values, the central value. And so this cosine of 45 was square root 2 over 2. Again, you can look that up, but this is how you can do this by memory. So we've computed cosine of 135 is negative root 2 over 2. Okay, maybe another time stamp. Right, 1830. So what we just did for that one particular angle, cosine 135, is a general procedure that we're going to undertake whenever we want to compute the cosine, sine, or tangent of any angle. So we're going to find the reference angle. We're going to decide on the appropriate sign, that is plus or minus, for our trig function. And we do that by just figuring out what quadrant the angle is in. And then we're going to compute the trig function on the reference angle and possibly adjust its sign, that is, its plus or minus. Examples might help. Okay, so we'll work in radian measure first. We'll do several examples in radians, and then we'll switch over to degrees. So in radians, there's this very nice feature about trying to figure out the reference angles. So I'll tell you what it is, and examples will help. But if your angle has this form, k pi over n, then the reference angle is going to be pi over n. And to decide what quadrant your angle is in, what you're going to do is add and subtract pi over n to your angle. And one of those two values will turn out to be a multiple of pi. And that'll tell you help tell you which quadrant you're in. So let's do that for some examples. Okay, so we're going to try to find the cosine of 3 pi over 4. Okay, so this is something pi over 4. So the story here that I was saying in symbols says that the reference angle is guaranteed to be pi over 4, the medium angle, the medium steepness. Okay, so now we're going to take 3 pi over 4 and we're going to subtract and add pi over 4. Okay, so when we subtract pi over 4, we get 2 pi over 4. That's pi over 2, and that's not the x-axis. When we add, we get 4 pi over 4, and that's pi, and that's the negative x-axis. Okay, so we've identified the side of the x-axis that our angle is close to. It's close to pi, but it's less than pi. So that tells us that our angle, 3 pi over 4, is in Q2. We've come around past 90, entered into quadrant 2, but we have not yet hit pi, so we're in quadrant 2. Okay, so we're going to use our little memory tool. We're in quadrant 2 that says that the sine is positive, and it's the only one of the 3 functions that is positive, so the cosine will be negative. Okay, so the cosine of 3 pi over 4 is going to be the same as the cosine of the reference angle, which we figured out, except there'll be a negative in front. Okay, so again, just by memory, the medium steepness has the medium value for cosine, root 2 over 2. Let's try another. Okay, so this time we're in some 7 pi over 6, so the reference angle is guaranteed to be pi over 6. This is the shallow angle. Okay, again, we'll do our two values here. We'll add and subtract pi over 6. So when we add, we get 8 pi over 6, and that's not a multiple of pi, so it's not on the x-axis. When we subtract, we get 6 pi over 6, and once again, we've hit that that's the negative x-axis. So this angle is close to the negative x-axis. This angle is actually bigger than pi, though. So this angle has swept past pi and gone down into quadrant 3. So that's how we figure out what quadrant we're in. Okay, now that we know what quadrant we're in, we use this little memory tool again. So, oh, the tangents are positive down in quadrant 3. That says that the sine will be negative. Okay, so the sine of 7 pi over 6 should match the sine of the reference angle, except it needs to be negative. Okay, so let's work through the memory again. This is a shallow angle, and the sine is talking about the y-coordinate. So we want a small y-coordinate, and that'll be 1/2. The y-coordinates get bigger as the angle gets steeper. Y-coordinates start out, or sine starts out at 0, and then when we get to the shallow angle, the sine is bumped up to 1/2. All right, one more radian measure. Okay, this time we're in a multiple of pi over 3. And so again, guaranteed that the reference angle is pi over 3. We check, we add. That's not a multiple of pi. When we subtract, we get 6 pi over 3. That's 2 pi. And that's an even multiple of pi, so this time this is the positive x-axis that we're close to. Okay. This 7 pi over 3, that was in fact bigger than 2 pi. 7 pi over 3 was bigger than 6 pi over 3. So this 7 pi over 3 has gone all the way around past 2 pi and come back into quadrant 1. Right? In quadrant 1, using our little memory guide here, all of the trig functions are positive. So the tangent will be positive here. Okay, so the tangent of 7 pi over 3 will match the tangent of pi over 3, the reference angle. And this time we don't make an adjustment because this one is supposed to be positive. Okay, so the way I do the tangent is by taking the sine divided by the cosine. This was a steep angle, so we want a large value of the sine, that's the y-coordinate, and we want a small value of the cosine, that's the x-coordinate related thing, which is small when the angle is steep. And this ratio comes out to be √3. Okay, let's try the degree measure. So I don't have a real easy guide for computing the reference angle this time. So what you have to do is just by arithmetic, just figure out what's the closest multiple of 180 to the angle you were given. Sometimes it's fairly easy, like find sine of 210. Well, it's pretty clear that 180 is going to be the closest multiple of 180. And so to get the reference angle, you simply do the subtraction. Your angle minus the closest multiple of 180 comes out to be 30. And that's the shallow angle. Now, 210 is bigger than 180, so this angle has gone past 180 and is now in quadrant 3. Okay. Using the little guide here again, tangents are positive, so the one that we want, the sine, will be negative. Okay. So the sine of 210 is going to be negative the sine of the reference angle. This is a shallow angle, so the sine should be 1/2. That is the sine of 30. We have to put the negative in front to get the sine of 210. Okay, so here's, like I said, where the degrees get a little tricky. 495. It might take you some arithmetic to try to decide that, in fact, 3 times 180 is as close to 495 as you can get as a multiple of 180. 2 times 180 is 360, and that's not quite as close, but it takes a little more work. Okay, because this is an odd multiple of 180, this is the negative x-axis. We've gone all the way around 360 and another 180. That's 540. Okay, so we do the subtraction, and our reference angle turns out to be 45, the medium steepness. Our actual angle was less than 540, so it was less than coming to the negative x-axis, and that means we went all the way around but didn't quite make it back down to the negative x-axis again, and that says we must be in quadrant 2. Quadrant 2, sines are positive, so the cosine is negative, and that's the finish here. We need to pick up a negative sign because of the quadrant we're in, and as the medium angle, we get the medium value for cosine. Okay, one more timestamp. We're at 2830. Trig identities. So these trig identities you've already seen because I've tried to coach them for you already. Instead of writing secant and cosecant as ratios, out of the gate I tried to write them as a reciprocal. Tangent, trying to encourage you to compute that as sine over cosine, and cotangent will be the reciprocal of that. Okay, the Pythagorean identities here, this first one you should have memorized and never lose track of it. And the other two you can memorize or have on a note card, or else just be able to derive them. The first thing about this notation, sine squared theta is a shorthand for sine of theta squared. So I don't know where that came from, but you just have to be able to interpret what that means. Sine squared by itself is a little ambiguous, but it's meant to be the sine of theta quantity squared. Okay, right, so the first one, I'm suggesting you just try to memorize it, but I guess I should derive it just the first time here anyway. we take sine squared plus cosine squared. Remember that sine is y over x, cosine is y over r, cosine is x over r. We square out, we simplify, and x squared plus y squared winds up being r squared, and that's because of the Pythagorean theorem. All right. Again, just memorize that one. I won't ask you to derive it, but just don't lose track of it. For the other two, the tan squared plus 1 is secant squared, and the other one, less common. What you should do is take the one that you've memorized and divide through by cosine squared. And when you do that, sine over cosine becomes tan, and it's being squared. The cosine squared over cosine squared, well, that's 1. And then 1 over cosine, you just need to remember that that's secant. And I won't do it, but I'll tell you that the third Pythagorean identity comes from dividing through by sine squared. Okay, so we're going to use these Pythagorean identities to express one trig function in terms of another. So here's the example. We are asked to express sine in terms of cosine, and then here's an important little proviso for angles in quadrant 3. Okay, so we're going to try to write sine as some formula that has cosines in it. So what we're going to do is start with the identity that involves both sine and cosine, and we're going to solve this identity for the sine function. Okay, so sine squared theta, we just subtract over. This is 1 minus cosine squared theta. And, oh, yeah, sorry, now I see it. So we want an identity involving sine and cosine. And just to be clear, when we say express A in terms of B, it means we want to write A equals some formula with B's in it. Okay, so to express sine in terms of cosine means we want to solve this equation for sine. So first step, what I just did, and then second step, take the square roots. Oh my gosh. Really startled me. I don't know what key I hit, but it wasn't the one I meant. Minus cosine squared, escape theta. Okay, so now that we've solved for sine of theta, we need to decide whether to take the plus or the minus. We can't leave it as either or. We need to pick one or the other. And that's where the proviso here for angles in Q3 plays a part. So for angles in Q3, the sine of theta should be negative. Tangent is the only positive one. So the formula for sine should be the negative square root of 1 minus cosine squared. Okay. One more idea here. We're going to try to evaluate some prescribed trig ratio in a quadrant other than Q1. We've done this once or twice when the angle was acute, but now we're going to be told that our angle is in Q2, the second quadrant, and we're going to be told that the tangent of that angle is negative 2/3, and the goal is to find the cosine of this mysterious angle. Okay, so this is how you go about a problem like this. The first thing you do is ignore the minus sign. What you're going to do is draw the acute angle in quadrant 1 that has a tangent of positive 2/3, right? And this angle will in fact be the reference angle for theta, right? So I'll label it as theta bar, and now we'll try to get the sides labeled correctly. So the opposite should be 2, the adjacent should be 3, and the hypotenuse, using the Pythagorean theorem, should be square root of 9 plus 4. That's square root of 13. Okay, so that's step 1. And then the second step is to compute the cosine of this reference angle. Okay, so cosine, so we're back to a right triangle, so we can just use adjacent over hypotenuse. So this would be 3 over square root 13. Okay, so why did we compute cosine? It's because we've been asked to find cosine. Okay, but we want the cosine of the angle theta that's in quadrant 2. We've got the cosine of the reference angle, but we want the cosine of the angle itself. And to do that, we might have to adjust the sign, that is the plus minus. All right, in quadrant 2, Q2, let's see, all students take calculus, bold. The sign is positive, cosines are negative. So, the cosine of this original angle that we were asked about, the one that's in Q2, I copied and didn't paste, needs to pick up a minus sign over the angle that we just computed the cosine of. All right. Oh my goodness. The really good news is that the next topic is quite short. So we're at 36. I don't know how that happened. Okay, so this is a beautiful little formula. It'll become your friend. You'll like it a lot, I think. This is how to compute the area of a triangle when you know two side lengths and the angle in between those two sides. Okay, so here's the blue box. The area is 1/2 AB times the sine of the angle. Why? Well, just a quick picture. I've drawn, so here's my triangle, side lengths A and B, and the angle theta in between. I've drawn the triangle so that A is the base of the triangle, and in order to get the area, what we need to do is find the height of this triangle. Okay, so if we look at the sine of this angle as a right triangle, as an angle in this right triangle, the sine of theta would be h, the opposite, over the hypotenuse. And we can solve this equation to find that the height of this triangle is b sine theta. Okay, so the area is 1/2 the base times the height, and the height was b sine theta. All right, we're going to use the formula and then we're done. So find the exact area of this triangle and fully simplify your answer. Okay, so the players are 10, 3, and sine, and angle 120. So the area is going to be 1/2 10, 3, sine 120 degrees. Okay, and that's the exact answer, and that's correct, but it asks to fully simplify your answer. So to do that, we're going to evaluate sine 120. All right, so reference angle is 180 minus 120 equals 60. This angle is in quadrant 2. All students take calculus. Sine is positive. So sine of 120 should match exactly the sine of 60. Oh, this is the steep angle. I should have written that. So this sine is root 3 over 2. Oof. Root 3 over 2 is what we're going to put in. And let's see. I think we'll leave this as 15 root 3 over 2. And that'll be our simplified form. Okay, thank you for sticking with me. We'll see you again in section 5.4.